Okay. So in the first part, we have the first law of motion. In not many books, they talk about this motion too much because we don't have like a formula for this, but it's good for us to know about it. The first law of motion is also known as the law of inertia. Inertia is related to the object's mass. As an example, I'm going to ask you something. What do you think is easier to push? A chair in the from the living room, for example, or a car? What do you think is easier to push for you? I mean, you can push
Sure.
any object, but how many objects would you be able to move? I mean, pushing successfully. Okay, as Emma said, it's probably easier to move a chair. I have a chair that is really difficult to move, but that's another story. I mean, normally a chair is easier to move than a car, okay? Because you can see when someone has issues with a car, they need to call more people to help pushing the car to moving away from the street. I mean, from the highway. So that happens because more massive objects are more difficult to move. And that is related to the law of inertia. Inertia itself is not moving objects. That's more related to the second law, but inertia is related to the object's mass. For example, if someone is riding a bicycle and you are walking with your phone and you are listening to music and you don't hear that the bicycle is approaching you. So the bicycle hits you. How much is it going to hurt? Situation two. You are walking down the street, listening to music, you don't realize a car is coming. The car hits you. Rip. No, I'm sorry, no, no, that is not true. But almost rip, okay? Almost rip. So what happens? It is more likely that you survive to a bicycle crash accident than a car crash accident. The reason is because the car is more massive. The car is more massive. So that is important that you know. The more massive an object is, more inertia. And more inertia means that it's more difficult to move, or once the object is moving, it's more difficult to stop. We're going to talk about this later. I'm going to read the slide better because then I get too excited about something that I need to say. The first law of motion is the law of inertia. It postulates that if a body is at rest, okay, or it is moving in a straight line, it will remain at rest, or it will remain moving in the same direction unless it is acted upon by an outside force. In other words, a cat was sitting on a table, the cat will be resting on the table. Pretty obvious, right? Unless the cat decides to move, or unless you move the cat away from the table. Gato chuco este is get away from here, I need to eat, or something like that.
That will be the outside force.
Exactly that. You pushing the cat away. Never do that to a cat, please. More respect for the cats because we love them because they are beautiful. They are perfectly created creatures. But in the end, when you push away the cat, you are applying the outside force that is changing um, the condition of the object, the condition of the cat. The cat was at rest. You push it away. Now, imagine Usain Bolt. Do you know who Usain Bolt is?
A runner.
Okay, he runs, he's very athletic, he's the fastest man alive. Okay, imagine that he's running I don't know. I'm not going to say a marathon because I don't think that's the kind of sports that he practices. But let's say that he's going to, because I think he is like more responsible for the 100 meters race. But let's say that he's going to participate in that race, okay? 100-meter race. So he's running, of course, because that is a competition. He's not going to walk. So he's running in a straight direction, 100 meters. And then a cat, sorry, I mentioned cats too much, but imagine that a cat is crossing in front of him. So,
Great.
no, 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 Sarah, qué barbaridad.
He's running. He was running. He will not see the cat. Wait
No,
for the
he's
cat.
going to
Sorry.
stop. No, he must stop. Come on. Okay, the cat is right in front of him. So he's coming with a velocity, with a speed, a really high speed, because he is the world champion at that race, precisely that race. So the cat is in front of him. It is very difficult for Usain Bolt to stop because he doesn't want to hit on a cat because everyone loves a cat. But it's very difficult. So how difficult is for some object or for a person who is at a really high speed to stop? It's going to depend on the person's mass, on the object's mass. That's why in I don't know if you have seen, I guess you have seen that there in El Peaje de Santa Cruz, there are many accidents because the trucks can't stop and they crash cars. Okay, I think you have heard about it, and people say no, se quedó sin frenos. Yeah, it's true. But more importantly is that a truck that size is very massive. Plus, in the container, it's keeping things that are probably very heavy, okay? Because, transportation, that's the point of it. Okay? You're going to transport things from one place to another, and those things are massive. They have mass. They're heavy to lift. So, once the truck has brake issues, it should stop. Not because of the brakes, it's because of the inertia. Is the inertia the responsible of all those? Okay, terrible design also, terrible design. The person who decided to put the peaje over there, it's the more responsible of all the car accidents. But the reason why they cannot stop is because of the inertia. Very massive objects are very difficult for them to stop. That's why That's why when I am driving, I'm a good driver, in my opinion, a very good driver. I like speed. I travel at a good speed because I don't want to be like the typical lady, very slow lady who's driving a car. And no, I'm not that kind of person. But if I see a truck coming, okay, I never step in front of them, because I know that inertia could kill me. That's why I'm very respectful for that. Because I understand the magnitude of how important is that people respect um, a distance. It's very important for that reason. A tiny car like a Cucarachita Volkswagen, I can stop very easily. It's totally possible, but not for a truck that size. That's why the first law of motion is related to the mass. The more massive object, the more difficult to stop once it is set on motion. And Of course, it is also more difficult to change the direction of the object. That's the first law. The second, I talked too much, sorry. The second law is the one that we're going to work a lot with. It's the second law, okay? Take a look at the picture, okay? Those two kids playing like Daniel El Travieso card, okay? So this second law of motion, did you watch Daniel El Travieso when you were little? Okay, I'm too old for this. I'm sorry for being too old from a different generation. Anyway, the second
I
law.
saw it when I was little.
Ah, nice. So you're
Hey,
taking
97.
away Howell from me, and now you're telling me. I'm joking. The second law of motion is related to that kind of situation. You are actually moving objects. Okay, and when you move an object, you are accelerating the object. I mean, when you change the position of something, when you push something, you are having or you are adding acceleration to the general situation. Example, I need to push a car because, well, I run out of gas, for example, so I need to push the car away because it's blocking the street. So I'm gonna start pushing it. My purpose is to move the car. So the car was at rest, and once I push it, of course, with other people's help too, I'm gonna start moving the car. So the object was at rest. After pushing it, it's moving. That is a change in the object's motion. That is related to how much you can affect the acceleration of an object. So the second law of motion states that the momentum of a body is equal to the product of its velocity and mass. In other words, the force that I need to move the object is going to depend on the mass. For example, if I need to move a car, that car is going to affect on how massive it is. And I know that I already said it in inertia, but in inertia it's not like you can calculate the inertia of something. You can estimate the inertia of something by just taking a look to the mass. But here in the second law, we actually calculate the force required to move objects because we know the mass of the object, for example, so you know how much force is required to move it. That is the second law of motion. And also the forces are vector quantities. That means it matters where the force is going. For example, if I push the car, I push it forward, so my car is gonna, I'm going to apply the force on it, and that force is going in the forward direction. Okay, that's why vectors are so important in physics because we care about where objects are going. And the third law of motion is this is beautiful. I love it. Is known as the law of action and reaction. Okay, so somebody smiles at you and you smile at him back, for example. Okay, the action, smiling face. Reaction, you also smile. So this third law of motion states that when two bodies interact, the force they apply to each other is equal in magnitude and opposite in direction. In other words, if I'm playing, for example, um, well, who plays like that? But I remember I used to do it, so probably you have experienced this situation before. So I'm playing with a classmate and I'm pushing him, okay? So the reason why I cannot move him is because he is probably applying the same force as me, but in opposite direction. Imagine that I want to They're gonna be pushing a desk, a very heavy desk made of wood, for example. If I push it, yes, it's going to be hard for me to move it, but in the end, I will move it. That means that the force that I apply on the desk is bigger than the desk weight. Now, imagine that I'm gonna push a wall, okay? The front wall of my house. I'm gonna push it. I'm gonna spend hours pushing it. And by the end of the day, the wall won't move. That is impossible to happen unless the condition of the house or the wall itself is terrible. But normally you cannot move a wall because it's too massive. And because the reaction, just because the wall is massive, is applying a reaction against you. You are pushing it, and the wall is like saying, "I'm here. Not you're not gonna move me." So mass matters in these topics. The more massive the object is, more force is required to move it. The more massive an object is, more inertia. And the third law of motion is the action reaction law, and that means that every object is going to oppose a force against the initial force applied. That is always going to happen, but that those forces, when they are not the same, is when you move objects, for example. But when they are the same, we say that the objects are at equilibrium. So in this moment, I'm going to, okay, now this part of the infography is interesting, and it's like more updated information. Um, by the time Newton discovered, when he establishes these the three laws of motion, um, it applies for almost every object or every kind of body. But now with quantum mechanics, I mean, when I say quantum mechanics, I'm terrified about it. But in the end, what happened with quantum mechanics is that it establishes that the three laws of motion are okay unless objects are moving at the speed of light. Then the Newton's laws cannot be applied to objects that are moving at the speed of light. So for example, in the universe, okay, other kind of laws of motion need to be applied because, of course, a planet is a lot more massive object, and I don't know if you know what the speed of light is, but it's very, very, very fast. Sorry. Um, in case I just didn't know, is 300,000 meters per second. That's a lot. Imagine in 1 second you are moving 300,000 meters. That's so fast. So for those kind of objects, they're going to be like the exception of the rules. But here on Earth, the three laws of motion from Newton's law are going to be applied. So let's see. I'm going to show you a video that I really like. Let me see if you understand her accent. I understand her accent, but people tell me sometimes that cannot. That's why I turn the subtitles on. didn't share the sound.
We've been talking a lot about the science of how things move. You throw a ball in the air, and there are ways to predict exactly how it will fall. But there's something we've been leaving out: forces, and why they make things accelerate. And for that, we're going to turn to a physicist you've probably heard of: Isaac Newton. With his 3 laws published in 1687 in his book Principia, Newton outlined his understanding of motion, and a lot of his ideas were totally new. Today, more than 300 years later, if you're trying to describe the effects of forces on just about any everyday object, a box on the ground, a reindeer pulling a sleigh, or an elevator taking you up to your apartment, then you're going to want to use Newton's laws. And yes, I'll explain the reindeer thing later. Newton's first law is all about inertia, which is basically an object's tendency to keep doing what it's doing. It's often stated as an object in motion will remain in motion, and an object at rest will remain at rest unless acted upon by a force. Which is just another way of saying that to change the way something moves, to give it acceleration, you need a net force. So how do we measure inertia? Well, the most important thing to know is mass. Say you have 2 balls that are the same size, but one is an inflatable beach ball and the other is a bowling ball. The bowling ball is going to be harder to move and harder to stop once it's moving. It has more inertia because it has more mass. Makes sense, right? More mass means more stuff, with a tendency to keep doing what it was doing before your force came along and interrupted it. And this idea connects nicely to Newton's second law. Net force is equal to mass times acceleration. Or, as an equation, F net equals ma. It's important to remember that we're talking about net force here, the amount of force left over once you've added together all the forces that might cancel each other out. Let's say you have a hockey puck sitting on a perfectly frictionless ice rink, and I know they're not usually perfectly frictionless, but stick with it. If you're pushing the puck along with a stick, that's a force on it that isn't being cancelled out by anything else, so the puck is experiencing acceleration. But when the puck is just sitting still, or even when it's sliding across the ice after you've pushed it, then all the forces are balanced out. That's what's known as equilibrium. An object that's in equilibrium can still be moving, like the sliding puck, but its velocity won't be changing. It's when the forces get unbalanced that you start to see the exciting stuff happen. And probably the most common case of a net force making something move is the gravitational force. Say you throw a 5-kilogram ball straight up in the air and then, get out of the way because that could really hurt if it hits you. But the force of gravity is pulling down on the ball, which is accelerating downward at a rate of 9.81 meters per second squared. So the net force is equal to ma. But the only force acting here is gravity. This means that if we could measure the acceleration of the ball, we'd be able to calculate the force of gravity. And we can measure the acceleration. It's 9.81 meters per second squared, the value we've been calling small g. So the force of gravity on the ball must be 5 kilograms, which is the mass of the ball, times small g, which comes to 49.05 kilograms times meters per second squared. We use this equation for gravity so much that it's often just written as Fg equals mg. That's how you determine the force of gravity, otherwise known as weight. Now, those units can be a bit of a mouthful, so we just call them newtons. That's right, we measure weight in newtons in honour of Sir Isaac, and not in kilograms.
Okay, so far, she has mentioned about inertia, basically pretty much accurate to what I said before. Second, where she's talking about the second law of motion, and she already gave you a formula, which is the weight, or the force due gravity. Force due gravity, also known as weight, has a formula that is equal to mass multiplied times gravity, the acceleration due to gravity. And in what unit are we going to measure it? As she already said, newtons. Remember when we were working with vectors, I draw a lot of vectors, and they were measuring newton or pounds, okay? Both are used to calculate weight, okay? But the international unit for weight is Newton. So that's why for this kind of topics, all forces that we need to calculate will be in Newton. Okay?
Kilograms are a measure of mass, but
Sorry. That's something that I also wanted to say. It's not the same saying weight than mass. I mean, both are different words. I know that when you go to La Pulperia and you say, give me a pound of rice or 1 kilogram of rice, they can sell it to you. But kilogram is a measure of an object's mass, not the weight. So I know that is a misconception because we say, no, yo peso 50 kilos. That's a pretty common comment, okay? And it is a misconception because kilos is a measure of mass, not of weight, okay? But there's like an allowance in body weight, for example, that could be related to the mass in kilograms or grams or pounds. That's why. But the real name for your weight, your real weight, should not be measured in kilograms, but it is easier. It is easier because, well, all objects can have a measure of the mass, could be in kilograms, but all weight are multiplied by gravity. That's why the allowance of using kilograms to express weight, but in physics is different, okay? In physics is kilograms for mass, newtons for weight.
Gravity often isn't the only force acting on the object. So when we're trying to calculate a net force, we usually have to take into account more than just gravity. This is where we get into one of the forces that tends to show up a lot, which is explained by Newton's third law. You probably know this law as for every action there's an equal but opposite reaction, which just means that if you exert a force on an object, it exerts an equal force back on you. And that's what we call the normal force. Normal in this instance means perpendicular, and the normal force is always perpendicular to whatever surface your object is resting on. At least it is when you're pushing on something big and macroscopic, like a table. If you put a book down on a table, the normal force is pushing and therefore pointing up. But if you put it on a ramp, the normal force is pointing perpendicular to the ramp. Now, the normal force isn't like most other forces. It's special because it changes its magnitude. Say you have a piece of aluminium foil stretched tightly across the top of a bowl, and then you put one lonely grape on top of it. Because of gravity, that grape is exerting a little bit of force on the foil, and the normal force pushes right back with the same amount. But then you add another grape, which doubles the force on the foil. In that case, the normal force doubles too. That'll keep happening until eventually you add enough grapes that they break through the foil. That's what happens when the normal force can't match the force pushing against it. But what does Newton's famous third law really mean though? When I push on this desk with my finger right now, I'm applying a force to it, and it's applying an equal force right back on my finger, one that I can actually feel. But if that's true, and it is, then why are we able to move things? How can I pick up this mug? Or how can a reindeer pull a sleigh? Basically, things can move because there's more going on than just the action and reaction forces. For example, when a reindeer pulls on a sleigh, Newton's third law tells us that the sleigh is pulling back on it with an equal force. But the reindeer can still move the sleigh forward because it's standing on the ground. When it takes a step, it's pushing backward on the ground with its foot, and the ground is pushing it forward. Meanwhile, the reindeer is also pulling on the sleigh while the sleigh is pulling right back. But the force from the ground pushing the reindeer forward is stronger than the force from the sleigh pulling it back. So the animal accelerates forward, and so does the sleigh. So one takeaway here is that there would be no Christmas without physics. But now we have an idea of some of the forces we might encounter, let's describe what's happening when a box is sitting on the ground. The first thing to do, which is the first thing you should always do when you're solving a problem like this, is to draw what's known as a free body diagram. Basically, you draw a rough outline of the object, put a dot in the middle, and then draw and label arrows to represent all the forces. We also have to decide which direction is positive. In this case, we'll choose up to be positive. For our box, the free body diagram is pretty simple. There's an arrow pointing down, representing the force of gravity, and an arrow pointing up, representing the force of the ground pushing back on the box. Since the box is staying still, we know that it's not accelerating, which tells us that those forces are equal. So the net force is equal to 0. But what if you attach a rope to the top of the box, then connect it to the ceiling so the box is suspended in the air? Your net force is still 0 because there's no acceleration on the box, and gravity is still pulling down in the same way it was before. But now the counteracting upward force comes from the rope acting on the box in what we call the tension force. To make our examples simpler, we almost always assume that ropes have no mass and are completely unbreakable. No matter how much you pull on them, they'll pull right back, which means that the tension force isn't fixed. If the box weighs 5 newtons, then the tension in the rope is also 5 newtons. But if we add another 5 newtons of weight, the tension in the rope will become 10 newtons. Kind of like how the normal force changes newtons of
Okay, I want to say something.
Weight, the tension in the
She's mentioning that when the box is on a surface, okay, you will have a normal force, okay, which is opposite to gravity, okay, and it's always perpendicular to the surface. But once you put the box hanging from a rope, you have no more normal force because the object is not standing on a ground or on a surface, okay? So normal force exists or is applied only when the object is placed over a surface. That surface could be the ground or a table or whatever surface, okay? Now, but when an object like this box is hanging from a ceiling, like over there, what is keeping the object in place is the rope, okay? And now, the normal is not taking part of it, but the tension force. And the tension force is going to be always equal, but in opposite direction to the gravity, just like the normal, okay? But it's a tension force because we have a rope, okay? So whenever you have a rope, we're gonna have tension forces. So I'm going to send this video to Classroom so you can finish to watch it. So in next class that we have the quiz is gonna be just theory about the 3 laws of motion. Okay, and I'm also going to send